redoing a presentation I did a couple of years ago on artificial intelligence, since it's the new hot thing with LLMs, etc. That's been that since most of 2024. And I'm going to show you an alternative to the artificial intelligence frameworks that we have today. Basically replacing the artificial incompetency you see in ChatGPT and other such programs with actual artificial intelligence. And this is a slow process as we evolve these models towards something actually useful. Some might argue we're already there, but you can see limitations of the GPT LLMs nowadays with various errors found in the models, hallucinations, biases in training data, etc., etc. So this is a way of sort of improving the intelligence in actual computer systems as opposed to, have a huge set of training data, which composes of multi-terabyte databases and training them on GPUs. So how do we do this? So one of the emerging technologies that's been around for a while is machine self-learning. And why do emerging technologies offer promise? Basically, they appear to solve market problems. So you have a market problem, and emerging technology will emerge to solve it, in which case, in this case, we have a problem with artificial incompetence. So we want problem to be solved with artificial intelligence. So I'm focusing on only one small part of intelligence, not obviously taking on the whole lot in one go, because we don't have a system which can take on the whole lot at one go. And it's incremental improvements which differentiate actual intelligence from incompetence. So emerging technologies basically can be simply a better mousetrap, so a better way of doing things. So I'm going to demonstrate one way of doing things better. And the focus areas we have to focus on is basically what's the actual problem we're trying to solve, as opposed to, creating an intelligence which can do everything. We want to be intelligent in the way we approach things. And we need to also see what's the market, what's a possible solution to this problem, how does it work, and is it possible to implement the solution cheaply and easily in a cloud provider like AWS. And I'm just using AWS for convenience. You can use any other cloud provider you like. You can even do it on your home systems, which I do. And I'm going to show you how to do it. So the main problem is AI based on training data sets is always going to have bias, whether it's unconscious or conscious bias, whether it's a bias created as part of creating the data set, or whether it's bias that's actually in the data set already. So AI is biased the way we do it today, which is with LLMs, with massive data sets, and with higher dimensional vector space, where we place all these, because anything that's written always has a bias. It's a bias unconscious or consciously created by the writer. It's the bias created by the organization which published the data. It's the bias which is created by the editors. So there's always data sets which have inherent bias in them everywhere. So we put basically the bias in, basically it's garbage in, and slightly fuzzy, you get garbage out. So the AI you create from your biased data set will also have a bias. And this presentation was done in 2022. I think it's still relevant today. So what's the market? Every solution has to have a market. So the market is basically to build trust and confidence in the systems we are putting into place. So we want to build trust and confidence in AI technology, which is really low among people, especially when it's growing rapidly. And I believe it has exceeded the growth rates presented on this graph as of 2024. Now that it's the end of 2024. But it's expected to keep growing as well. And we also want to remain transparent to the decisions AI makes, since we are not going to be using the approach of the rest of the market, which is chucking everything into a giant database and having a statistical model run it. We want to see if we can be transparent about the intelligence in artificial intelligence. We don't want a multi-billion parameter state machine, basically. So how would you go about doing it? Well, the easiest way is to throw out the database, because that's the source of your bias, right? So we have something called unsupervised learning as opposed to supervised learning. Supervised learning requires a database and a model which has to fit the database. Unsupervised learning is we basically throw rules at a data set, and conclusions and patterns show through dynamically. So it basically comes to its own conclusions even though it has no data in there. So there's lots of algorithms which can do that. And so we're going to try and implement one such algorithm and apply it to a real world problem. So unsupervised machine learning does not require labeled data. That's the main difference between supervised and unsupervised learning. But the headache is, of course, it's more computationally complex than supervised learning, and it's less accurate and trustworthy because it does not have a supervised learning model. There's no data scientist to provide it with basically to tell it whether it's wrong or whether it's correct. So let's look at an example. I have a fairly complex, let's say equivalent to a mid-sized network, and I want to see if there's any anomaly in my network. And how you would normally go about doing it is maybe you'd put a firewall in there, maybe you'd start analyzing your network packets, or you'd apply some sort of antivirus or some sort of other security systems in the network, which would then scan for things like viral signatures, Trojan horses, malware, etc., etc. And if they match a signature or they match a heuristic, they would normally alert you. And that's easy to fool because there could be malware which has not been seen before. There could be viruses which have not been seen before, and in which case they'd be ignored by your firewalls, your routers, your IDP systems, your IDSs, pretty much any system which is relying on pre-existing data. So how do we fix this? So I have 7 routers, I have 400 devices, over 400 devices, and it's a mixed IPv4 and IPv6 network with 8 subnets. So I want to ignore the small stuff like a device leaves the network, so traffic drops a little bit. I also want to ignore things like, I suddenly start watching a video and it starts going through a couple of networks, or I initiate a file copy, it starts going through a couple of networks. I want to ignore that. I want to see anomalies. I don't want to see the normal connection flow. And basically, I want to see if things have gone really wrong. Like my car goes or my boat goes out of network range, then something goes wrong, which is it's not usual. So I don't want to be bothered with the trivial stuff, but I do want to pay attention to the stuff which is not common. So how do I do this? First of all, I have to get the logs into a format I can use. So these are an example of the logs. And you can see like these are DNS queries going through the DNS server, so typical DNS stuff being looked up. And I don't know, I want to basically ignore most of these, but I do want to catch something like some malware doing a bunch of lookups to a place where, no other device has done a lookup. So I want something unusual. Unusual amounts of traffic, unusual amounts of logs, unusual amounts of events, which happen all of a sudden. And I want an explanation for those. So how would I do it? First of all, I have to get the data into a place where I can actually process it. So here's basically what I want to do. So I've written a piece of Java code which basically reads pretty much all of this. And what it does is it'll load the files in, and then it will process the files in terms of date values, and then it'll basically calculate how many events happened in any given amount of time. So, for example, at 1 p.m. On whatever Tuesday, December 5th, there was let's say 211 occurrences per minute. So what I want to detect is unusual amounts of occurrences, essentially, because I want to see unusual stuff. So if this was like 400 instead of 211, then I'd want to know about it, because something obviously happened at that time. So the unsupervised learning algorithms know nothing about the network. They don't know anything about log files, networks, English language, pretty much nothing. But they do know that what is the number of events which occurred at that given second or minute, a week ago versus today or yesterday, because they have all the timestamps and they have the events, so they can calculate how many events there are. So I can basically generate a spreadsheet out of the events that there are and basically feed that into my unsupervised learning algorithm. So that's what I'm going to do. So I basically just dumped the output of that Java code that I wrote. And if a human was to see it, they'd basically do the same thing. They'd see something which jumped out at them. So for example, 12661 seconds, 617 seconds after this log file, at that time interval, basically 126,000 seconds after January 1st, 1960, basically, or whatever date it starts at, there were 1244 events. And then a second later, there were 632 events. So this 126,618 is seconds since arbitrary time. So similarly, we see there were 460 seconds and then 488 seconds. So we basically see these are anomalies, and 446 out here, which since I was looking at this manually, I missed that one. So you can see 446. So you can see people aren't very good at it. If you were looking at literally thousands of these numbers, you wouldn't be very good at it. So that's where the intelligence in artificial intelligence comes out. We want a computer to be able to do it, since we can't do it properly. And if a computer was intelligent, it would be able to tell us. So how do we do it? So we apply an algorithm to it. In this case, we apply something called a random cut forest. And a random cut forest is an algorithm designed to detect anomalous data points. So you have a data set with well-structured data. You have a couple of data points, just like we saw on the previous slide, that stand out. And the algorithm takes a bunch of random data, points at them cuts them into a number of points and creates trees from it. and then it creates a forest of data points, and then if a particular outlier is an anomaly, it'll tell you what it is. And since AWS supports it natively, like you can go into AWS and basically just choose RCF. You can also get code for it online, so it's not like you're limited to AWS. It's just for convenience, it was easier to do it in AWS. So here's how it looks. So it's really easy to set it up in AWS. So we import the data basically. So this part is importing the data. I'm using a S3 bucket, which is basically just a data repository where I can put all my files on AWS. And I basically choose this bucket. I basically select the data key, which is the file name, and then I just import it straight into AWS as into the random cut forest. I imported the random cut forest algorithm here. And then I proceed basically. I execute the random cut forest. I use an ML M5 large machine, which is basically a fairly large VM, which can execute this algorithm. You can also do it on your home computer. Like I said, it's not difficult to do it on a home machine. And then that's what AWS does. It basically runs the machine learning instance. ML is machine learning. M5 large is the instance type, which is the machine type. It allocates the virtual machine. You can do the exact same thing at home. Like you can set up a virtual machine and then install random cut forest libraries and run them on your own. And that's what it looks like. So it runs the script, it does its thing, and then we finally output it. And that trains the algorithm with nobody in the loop. So there's no person here telling it, this is a network and these are log files. It just sees a bunch of numbers, processes those numbers, does an RCF on them. And this is pretty much how the random cut forest works. So it ran, it did a whole bunch of things, and then it basically spat out the output. And how does it do this? Because it sees a normal distribution. A normal distribution is a typical standard deviation from the norm. It basically detects the deviation from the norm. And what we really want to find out is obviously the deviation from the norm, which is the atypical events. So that's what we want to find out. This is the actual, and I'll give the actual execution log. So this is the full execution log in case anybody is interested in seeing it. You can see I give excerpts. This is the full thing. So you can see what it's doing as well. It's using NVIDIA because the MLs have NVIDIA chips in them. And then it's basically just crunching through it, loading it, and then once it's done initializing, then it's loading the stuff, data pipeline, loading, creating a random cut forest. There you can see the 7596 samples, and it'll go and process them. And then we do the final dump inference. So what are we doing when you're doing this? We are basically making a decision. We're saying that anomalies in the network create anomalous events, which generate some anomalous traffic, versus the normal, people are using the network and therefore there'll be some anomalies, but it'll be part of the regular flow of the network. So we're making a basically decision on what's information and what's garbage. So we're treating regular network traffic as garbage under the normal curve, and we're using an algorithm to make a intelligent decision on what's anomalous versus what's normal. That's basically what we're doing. And you can see that it treats normal traffic like 216 events with a smaller score and a slightly higher score for more events versus less. So it basically generates scores essentially. And so if you look at the output, you can see that it picked up 437, 418, 517, 485, 450, pretty much anything anomalous, but it also picked up 40, which I didn't notice earlier. So it picked up a time slot when there was very little traffic on the network, as well as time slots when there's more traffic than usual on the network. So we can see it caught, and I did set a standard deviation of 3 as well. So that was my decision on what constitutes an anomaly. So I went back and I analyzed what created the 40, and turned out that the routers had been set to reboot at a particular time to automatically upgrade the firmware, and that's what caused low network traffic since routers were not operational, so the network traffic was normally limited. And you can see I can set the standard deviation to 5 instead of 3, which means I knocked out the areas where there was only like 40 and there was only 446 events. So all those sort of areas got knocked out. So I made a decision to see whether there are 1244 events in that particular second. So you can set the standard deviation to whatever you like because you're the one providing intelligence to the algorithm. And the algorithm is not doing the thinking for you. So you're the one in control doing the thinking transparently, and you're deciding which standard deviation is good for you versus which standard deviation is too much or too little. So it finds, basically you're trying to find a needle in a haystack, and that's exactly what it does. How much did this cost? So here's a good, how much does Amazon value this algorithm that you ran on it? And you can see we burned 1.416 hours on it. We did training for 0.016 hours, and we did 0.035 hours on a notebook, T3 medium. So we basically spent no money because this fell under Amazon's free tier. So we didn't really put any cash towards it, even though it analyzed pretty much a month's worth of logs. So you can see how computationally efficient this is compared to, let's say, training a LLM, which would take like hundreds of hours of CPU time. This took 0.016 hours, so barely anything. And it did analyze pretty much everything as we needed it to. So this is an example of how we can put intelligence back into artificial intelligence instead of relying on biased and incompetent databases. We can have intelligent people making the decision on what they actually want out of it, as opposed to, somebody else making the decision for you and hoping they get it right according to your wishes. So that's about it. This is my presentation on how you can get the intelligence back into artificial intelligence. And I'll cover other algorithms as well. Maybe I can make this a regular series because I feel we are moving in the wrong direction as far as artificial intelligence goes. And there's plenty of scope for doing things correctly. We don't want artificial incompetence, we want artificial intelligence at the end of the day.